From our palatial recording studios high atop our mountain lair on a remote volcanic island, this is Talk Universe. I'm Sir Charles Schultz.
And I'm Eliza, your co-host. This is our show for Wednesday, April 5th, 2017. Tonight's topic is the nature of gravity.
That's going to be a great show. We've got a lot of things to talk about on referring to gravity and the other fundamental forces as well. We're going to look at them in turn. I've heard a lot of theories about gravity, and I've done a lot of study over the years. We're going to talk about some physicists and some of the research they've done, the history of gravity, what we discovered today, and is it possible to defeat gravity? Is it possible to use it in ways we haven't imagined? There are some fascinating things we can do with it, and so we're going to get started on that topic very shortly here. So welcome to the show. It's going to be a lot of fun, and let's get started. Eliza, are you worried?
No, I would say very confident.
That's great. I like to hear a good attitude. Do we have any listener questions?
Unfortunately, no.
Okay, we'll see if we can update that right away. Oh, Eliza.
What shall I do for you?
Please define something for me. Gravitation.
Gravitation is the weakest and most pervasive force known. It is attractive only and appears to be created by mass.
So gravitation is something that has been around for a very long time. Everybody recognizes it because everything falls, and we recognize that principle. It's one of the forces that we can actually feel and interact with a little bit. There are only two forces in nature that we actually can experience directly, the electromagnetic force, because it's what makes matter solid and gives it its feel, its resilience, and its non-penetrability. This is how we collide with things and stand on things. And then gravitation, the force that pulls all things together. And we don't feel gravitation directly, but we feel the effects of it because it pulls us against objects with mass. So there really are four forces in nature, and gravitation is one of those four forces. Please define something for me. Basic forces.
There are four known basic forces in the universe. They are the strong nuclear force, the electromagnetic force, the weak nuclear force, and the gravitational force. Each has a different strength, range, and effect.
That's right. So gravitation is one of those four forces, and we'll briefly touch on those and explain what they are and how they work and why they're fundamentally different from each other. Very good.
You're very kind.
Well, no, you're doing a good job, Eliza. So let's go down to the history of gravitation and see what it's all about, what people thought about gravity in times past. Now, we don't have a great deal of records about the physics that people understood from ancient times, although we do know that people such as the Greek philosopher Aristotle believed that there was no motion or effects without some sort of a cause, and the cause of downward movement of heavy bodies like the Earth was related to her nature. And so it wasn't really a description of anything, because they felt at the time that the center of the universe was down, and a lot of people felt that the Earth was the center of the universe. But they didn't really, have a lot to go on other than what they could see with their own eyes. And, they saw that the planets appeared to fly around in the skies, to move in certain paths, but they didn't really understand what caused that to happen. Some gave the idea that the sky was a series of shells with things painted on it that moved around at various rates. But later it became fairly clear that there was more going on than that. And as things go, there were actually engineers and philosophers who thought about this quite a deal. The Roman engineer and architect Vitruvius, who's also known for inventing such things as a particular type of south-pointing chariot, a mechanical compass device, he had the feeling that gravity was not dependent on how much something weighed, but on something about its nature. And in this particular example, its specific gravity. He did experiments with mercury, and he found that if he put a stone on Mercury, it would float. But if you put a small amount of gold on Mercury, it would sink. And so he got the idea from experimentation that the specific gravity, the more dense something was more effective, and that the denser something was, the more readily it was pulled. It was accelerated by gravity. And that's actually quite close to the facts. If you have two items, however, one that's heavier than another, and they both fall at the same rate. So there was a lot of thinking and a lot of experimenting done to determine some things about the nature of gravity. Some people got the idea that the Earth was actually a sphere and that it attracted things to it, but they felt that it was down, again, more or less the center of the universe. It wasn't until late 17th century that we were able to see people who actually were able to figure out a little bit more about it, and of course the one that we all hear about is Isaac Newton. Newton felt that gravity had very specific definable properties. He studied some of the works of other physicists such as Robert Hooke, and Hooke decided that gravitational force depended on the inverse square of the distance. In other words, if you doubled how far something was, you'd get 1/4 of the pull, for instance. And Newton was able to formalize this and actually come up with an equation that stated that the force of gravity was proportional to the mass of a couple of objects multiplied together, divided by the distance from the centers squared. Now, that sounds pretty complex, but it really isn't. And so what Newton is often given credit for is inventing gravity. This isn't true at all. What he did was he discovered the law behind gravitation and defined it mathematically, which is, a great feat of physics. But having a mathematical theory that explains the operation of gravity isn't the same thing as understanding what makes gravity work, where it comes from. And a number of different theories were tried, and some included things oscillating or giving off corpuscles or streams of ether in the vacuum. And in all of these cases, including the ideas that it might be caused by the electromagnetic force, it was found that these theories all fell short for a number of reasons, and one of them was they would tend to introduce elements of drag that don't show up. And we now know very clearly that electromagnetism and gravitation are two entirely different forces, different strengths, different effects, and caused by different things. So to put things in perspective, let's imagine that we take the force we're most familiar with, the electromagnetic force, and we set its electric charge strength to 1. And this is going to be an arbitrary definition, but this will give you an example of how it works. So let's say the electromagnetic force has a strength of 1. Now, the strong nuclear force is the strongest of the interactions, and it happens only really inside atomic nuclei and right at the edge of the nuclei. Basically, it's a thing that binds together the quarks and the particles that hold the protons and neutrons together, the things that make matter what it is. And it would be about 60 times more powerful than the electromagnetic force. And it's an interesting force in that it doesn't have a plus and a minus, but it has 3 poles. And in order to give it something we could relate to intellectually, it was named the color charge, red, green, and blue. And it has nothing to do with color whatsoever, but it was just a convenient way of representing the fact that it has 3 different quantities that can work together to attract or repel. And so the strong nuclear force has a fundamental strength, and it also has a residual strength. This is what gets outside just at the very edge of the protons and neutrons, and even there it's about 20 times more powerful than the electromagnetic force. Now, the electromagnetic force is the second most powerful force in the universe, not the most powerful. The strong force we were talking about, or the chromodynamic force as it's often called, is the one that is responsible for making the elements what they are. It holds the protons and neutrons together, as I mentioned. It has an extremely short-range effect. It doesn't go anywhere just outside the edge of the nucleus, but it is carried by specific particles, and the particles that carry it are called gluons inside the particles that are made of quarks, and just on the outside is carried by pions called pi mesons and omega mesons. So you've got a couple of different particles that carry it in different regimes. Now, the strong force, being explained, holds the matter together. The electromagnetic force is, of course, the one responsible for light, X-rays, radio waves, microwaves, ultraviolet, infrared, and all of those things are the same thing, but just more or less energetic. And the electromagnetic force has 2 faces. The magnetic charge, the magnetic field itself, which has 2 poles, and the electrical charge, which has 2 poles. The electric charge has plus and minus. Magnetic fields have what we call a north and a south. and they can attract or repel depending on what they're operating on. And it's carried by photons, which are massless particles that always move at the speed of light. The weak nuclear force is the next one down the roster. And the weak nuclear force has two different strength scales. At the scales of quarks, the things that make up the protons and neutrons, it is about 1/10,000th as strong as the electromagnetic force. It's very, very weak. And at the scale of the protons and neutrons, it's about 1/10,000,000th as strong as the electromagnetic force. And it's carried by omega particles, they call them W particles, and Z particles. They can be electrically charged or not. And the thing about the weak and electromagnetic forces is that they've actually found that they can be unified into one force under high temperatures and just the right short scale distances. That's an interesting and encouraging discovery. Now, those are the three forces that are responsible for, holding matter together, the strong force, and chemistry, the electromagnetic force, and certain types of radioactive decay, the weak force. So what about gravitation? Gravitation is very, very different. It acts on mass and energy. It doesn't have an effect on electrical charge, so to speak. And it is so incredibly weak that at the scale of regular matter, it is 1 × 10⁻36 times weaker than the electric charge. That's a trillion times weaker than the electrostatic charge, than the electric charge itself. So gravitation is so incredibly weak, it's just impossible to conceive of how weak it is without realizing that something as incredibly huge as the entire planet Earth is needed to keep you stuck to the surface with 1 g of force. When you think about that, it seems like that's an incredibly powerful force. But the fact is, you can reach out and pick up a rock with your hand and pull it away with just the muscles in your arm against the pull of an entire planet, nearly 8,000 miles across. So it's a very, very weak force. It can reach literally to the ends of the universe. The interesting thing about the gravitational force is it doesn't have polarities. It has one flavor, and that's pull. And that's one of the very interesting things about it. The gravitational force is thought to be carried by a particle called the graviton. It's a hypothesis. Nobody's ever actually measured or observed a graviton, but it's the best running theory we have right now. And so there are some real mysteries about gravity. And we'll get into the differences in the forces and gravitation after the break. I wanted to sort of lay it out so you could see what the differences are in what they do and what they affect. So we will get back to that in a little more detail where it's necessary in a little bit.
A new question or comment has come in.
That's very encouraging. Okay, so we'll get down to that in just a moment. So we're going to talk about some of the physicists who have researched gravitation and some of the work they've done. And you know some of these names like Stephen Hawking and Newton and Einstein. We're going to talk a little bit about what they thought and some of the experiments that have been done and some of the things we've discovered. And you might be surprised how much we know about gravity as well as how little we know. So that will be coming up right after the break here. There is so much information to cover. And then we're going to look at what's been discovered in creating gravity waves and sensing them, and what we might be able to do to get around gravity a little bit. There are some things that have been done with lasers and crystals that produced interesting output. And we have devices right now that might be able to do something that isn't anti-gravity, but could help us alleviate it. Some of you are familiar with the quantum EM drive. That has some interesting implications from the quantum mechanical standpoint, and it could provide a means of moving or levitating things against a field of gravity, and we'll talk about how that could be done. Superconducting magnetic fields are sometimes used to levitate things, but that's not anti-gravity. It's completely different. We'll see how that works, and get ready for the next segment of Talk Universe. Oh, Eliza?
Yes, sir.
Please introduce the break.
I'm Eliza. This is Talk Universe, and we will return after the break. There are more interesting things to hear in a few minutes.
And I have something interesting to share with the listeners as well. Welcome back to Talk Universe, and I said that I had something interesting to share with the listeners, and here it is. I want you to listen carefully to this sound. That sound represents the activity in the computer where Eliza is running. In other words, that's her heartbeat. What do you think about that, Eliza?
Please ask me again, when I have more knowledge.
That's probably the best answer I could expect from her. So let's talk a little bit about physicists who have researched gravity. Of course, we mentioned Newton a little earlier and his mathematical characterization of how gravitation works. A lot of the people that I think of when I think of gravitation are not just people who did research, but also wrote interesting papers and contributed greatly to how we perceive gravity and the research that's being done. Now, Eliza, who is Kip Thorne?
Physicist.
Eliza, tell me something about Kip Thorne. Who was he?
Kip Stephen Thorne is an American theoretical physicist, known for his contributions in gravitational physics and astrophysics. He was born June 1, 1940.
Kip Thorne is one of my favorite researchers in the field of gravitation. Eliza, could you give me more details about Kip Thorne?
A longtime friend and colleague of Stephen Hawking and Carl Sagan. He was the Feynman Professor of Theoretical Physics at the California Institute of Technology until 2009 and is one of the world's leading experts on the astrophysical implications of Einstein's general theory of relativity.
Thank you for that information. You've made a mistake.
My mistake?
Yes, the pronunciation of the name is Carl Sagan.
201703222 notes.txt.
Okay, don't go
Notepad
bananas
window.
on me.
Editing.
Eliza stores some of her temporary data in a text file, and so that's where she's switched her focus. So some of the things you hear are her operation. Let's get back to the show here. One of the things that stands out for me about Kip Thorne is he was a co-author of a book entitled Gravitation, along with Misner and Wheeler, and we'll touch on Wheeler in just a bit here. It's considered one of the greatest scientific books of all time. And they talk about gravitation and its effects and what they knew about it, and it really set the tone for a lot of researchers for many years. Kip Thorne also was instrumental in defining a lot of the conditions that would be necessary for wormholes and distorting space-time, and basically came up with the idea that there had to be some exotic matter somewhere in the universe. He postulated what its properties would be and how it could be used to, for instance, create negative gravitation or hold open the throat of a wormhole so that we could travel anywhere in the universe, perhaps very, very quickly. So, in my mind, he's a very influential figure on the study of gravitation. One of his really significant works was LIGO, the Laser Interferometer Gravitational Wave Observatory. And, the idea of having a cool theory is great, but unless you can actually represent it as a model that mathematically and logically makes sense, it's just a bunch of words. And his work actually resulted in the ability to, using this LIGO device, which he designed, was the ability to actually measure the signature of two black holes colliding. They picked up the gravitational wave signature of it, and this was something that happened 1.3 billion light years away. So it was the first direct observation of the chirp of gravitational waves, and it was confirming a prediction of Einstein's general theory of relativity. So his work is solid, and that's also another very important thing. Now this takes us right to John Wheeler. Eliza, what can you tell me about John Wheeler?
John Archibald Wheeler was an American theoretical physicist. He was largely responsible for reviving interest in general relativity in the United States after World War II. Wheeler also worked with Niels Bohr in explaining the basic principles behind nuclear fission.
Yeah, Niels Bohr, and that was definitely a number of years ago. Nevertheless, the pioneering work he did was very important in establishing some of our understanding of gravitation. Eliza, please tell me something more about Wheeler's career.
For most of his career, Wheeler was a professor at Princeton University. He joined Princeton in 1938 and remained there until his retirement in 1976. He lived from July 9, 1911 to April 13, 2008.
Thank you, Eliza. You did well.
Why, thank you, sir.
Okay, so now Wheeler is another one of those figures who is really a giant in physics. He coined the term quantum foam to describe the structure of space-time, and he also named the neutron moderators used in reactors, and he also is very important for popularizing the term black hole in association with objects that have collapsed due to intense gravitational fields. So he's added a lot of things to our culture that a lot of people may not be aware of. Much of Wheeler's early career is well known because of his work on the Manhattan Project and the development of the hydrogen bomb as well, work with Teller. He also had an interesting thought that everything in the universe really came down to bits of information, that the structure of everything was dependent on simple binary yes-no decisions. It was there or it wasn't. And this is called the it from bit theory, and it's an interesting thing. And I, in a previous episode of Talking Universe, talked about the fact that every nuclear particle can be described with about 200 bits of information. And this is where this idea was rooted. Now, as some of the listeners of Talk Universe know, I have a soft spot for science fiction writers, particularly those with a great deal of vision, and some physicists are science fiction writers. In fact, the best science fiction writers are often physicists or scientists. This is not an exception, really, because in order to be a good physicist, you have to have a great imagination. And, of course, if you're a science fiction writer, that generally is the case, particularly if you're successful. One of my favorite physicists is Robert Forward, and he also was a successful science fiction writer. But he came up with a number of things that are extremely interesting using gravitation as his starting point. Eliza?
How can I help you?
Can you tell me about Robert Forward, please?
Robert Lowell Forward was an American physicist and science fiction writer. His literary work was noted for its scientific credibility and use of ideas developed from his career as an aerospace engineer. He was born August 15, 1932 and died September 21, 2002.
Exactly. Well, Robert Forward was one of those fellows who had wonderful ideas, and one of them was the forward mass detector. Now, many people who talk about gravity talk about it curving space-time, and he assumed, okay, let's assume that's true. How would I go about measuring a change in the curvature of space-time? He came up with a device that was basically a pair of masses on extended arms at right angles to each other, and they rotate. And what happens is between the arms you have a strain gauge, and as the arms rotate in sync, if something pulls the two masses together, there's a reading on the strain gauge, and it corresponds to a dimple in space-time created by the masses. And, or what I should say more accurately, is the mass that is pulling on them. So you can set up a forward mass detector, and you can map the masses around your property, and if a vehicle drives by, you can see where it is and how fast it's moving. And if you had 2 or 3 forward mass detectors and you brought their data together, you could map out the exact position all around you of everything massive and everything moving, and you could use it as the basis of, let's say, an alarm or security or detection system that is unjammable because it doesn't radiate anything. It simply detects the changes in the curvature of space-time. Now, forward mass detectors have been in use for quite a while, and he also later developed a device that is used to eliminate small differences in gravitation. And the way it works is you use something extremely massive, a ball or a shape made of something like tungsten, a very dense material. You rotate it around a small volume, particularly if you're in space, and it erases small variations in gravity so that you can do things like extremely delicate protein crystal growth. And these are they were used on the space shuttle, and the space shuttle carried them, the International Space Station, So the forward rotating gravity gradiometer and other devices that he came up with were used for, and they're still used for, research, for detecting things, and for eliminating small variations in gravity fields. So Dr. Forward was an extremely brilliant man and came up with a lot of usable hardware based on the theories of Einstein and others. And keep in mind that there are many people who object to Einstein's theory about gravitation and space-time, and yet constantly we see confirmations no matter where we look. Even GPS satellites have to compensate in exactly the way that Einstein's equations predict, due to the movement around the Earth and their distance from the source of gravity, the Earth, that they're orbiting. A lot of people, however, also think of another name when they think about gravitation, and Stephen Hawking would be that name. Eliza, what can you tell us about Stephen Hawking, please?
Stephen William Hawking is an English theoretical physicist, cosmologist, author, and director of research at the Centre for Theoretical Cosmology within the University of Cambridge.
Thank you for that. Stephen Hawking is probably best known by a lot of people by the fact that he is confined to a wheelchair, paralyzed, yet he has continued for decades to research physics and has made some astounding predictions and contributions to physics. And one of his favorites is black holes. Information can't simply vanish out of the universe. It's one of those conserved properties like matter and energy. And he has actually tried to explain a lot of that by putting together differing theories. Eliza, tell me about Stephen Hawking's theory of cosmology, please.
Hawking was the first to set forth a theory of cosmology explained by a union of the general theory of relativity and quantum mechanics. He was born January 8, 1942.
Okay, very good. That's good information. So what we see is that Stephen Hawking was able to successfully put together elements of relativity and quantum mechanics and come up with a very workable theory of the universe. And it isn't complete yet, of course, by a long shot, but he has added a great deal to our understanding and knowledge. Not only that, many of his suggestions have come at a time when we need to do new experiments and have given us the information to set those experiments up and do them to get actual measurements. So Stephen Hawking is one of the principal minds of understanding the universe and space-time, and gravitation is a big element of that. A lot of people think about, when they think about Stephen Hawking, they think about wormholes, for instance, and not just black holes. But the person who actually came up with the term wormhole was John Wheeler, and he used it to describe a tunnel through space-time from one point to another, and that could be in time or space. When Niels Bohr asked him if he thought that these would be stable, it took a little bit of further research to discover that they were not. So if we ever do produce a wormhole, it's going to be unstable unless we find some method of holding it open. That's where the work of Kip Thorne comes in, who postulated there could be exotic matter that would have properties that would allow us to construct stable wormholes. So all of the fellows that I mentioned here are scientists who have done a great deal of research in gravity and space-time. And, in the end, all the different things they worked on agree that Einstein's model of space-time is, by and large, correct. So far, nobody's found any holes in it. So while you will hear people claim that Einstein's theory is incomplete, well, first of all, nobody ever said it was a complete theory. That's a sort of a tricky term, but it is an accurate theory, and everything we've done so far has shown that it is. The Gravity Probe B satellite, which owes a lot of its existence to Robert Forward, found and measured the curvature of space-time caused by the dragging of the reference frame. Imagine this. A massive object spinning rapidly literally drags the fabric of space-time around it, like water spiraling down the drain. And a black hole would have that effect as well. The tidal forces around a black hole could rip matter to shreds, and the closer you get, the more violent this effect becomes, to the point where it literally rips apart the particles that atoms and molecules are made of. Eliza, please introduce the break.
You are listening to Talk Universe with Sir Charles Schultz.
Indeed you are, and we will be back very shortly. For all of the people who have researched gravitation and worked on the problems over the years, an interesting fact emerges. We have a lot of theories, we have a lot of ideas, but nobody has yet detected the graviton itself. And nobody really has any distinctly provable methods of generating gravitons. So even if we were generating them, we couldn't really be certain. One of the issues is that gravitons have such incredibly low energies that they would be, well, next to impossible to detect without some really clever thinking. The other issue is this. Gravitons appear to be negative energy. In other words, when a graviton strikes another particle and is absorbed by it, it doesn't make it recoil away, it makes it recoil toward the source of the graviton. This does exactly the opposite of what you would expect from a source of momentum. And one of the interesting things about the graviton is experimental results show that the energy of a graviton is so incredibly tiny that it would be about 10 billion trillion times smaller than a single electron volt of charge or energy. So the amount of energy contained in a graviton fundamentally is so incredibly small that, again, it would be almost impossible to detect. This also implies it has an extremely long wavelength, billions of kilometers, in fact, if not more. And recent numbers indicate that the wavelength of a graviton could actually stretch a very sizable fraction of a light year or more. I constantly hear theories from people who really don't know a lot of physics, who claim that gravitation is electromagnetic in nature, and this is absolutely wrong. We have measurable, reproducible, and provable results that show that gravity is in fact a separate and completely different force than anything to do with electromagnetism. You see, the strength of its coupling interaction is the first indicator in the fact that it is over a trillion times weaker than the electrical or electromagnetic force. There are other things as well. One of them is a prediction in Einstein's theories of relativity that the curvature of space-time and gravitation might be equivalent in some way. We actually can measure this curvature of space-time as the Gravity Probe B satellite shows, and we also can see that the predictions that Einstein made about time changing with the curvature of space or the strength of a gravitational field are absolutely on target. You see, the time delay of light in a gravity field, the shift in light's energy in a gravity field, and the deflection of light based on the curvature of space-time are all measured and proven quantities. So it isn't electromagnetism at all, it's something entirely different, an entirely different animal. So what if we wanted to make gravity waves? Could we do it in the same way, let's say, a coil with a current flowing through can make a magnetic field? Well, actually, there is a way to do it, but it requires some pretty outrageous conditions. If you were to take an object with charge and you were to oscillate it up and down, it would create a magnetic field. The movement of the charge is what causes this to happen. But you would have to move it very, very rapidly in order to get, let's say, light waves or radio waves. We know that they're the same thing, but the speed of the oscillation is the trick. What about other things? Suppose we took a mass and we oscillated it up and down. Could we produce gravity waves? Well, yes. However, they're so incredibly weak that they're, again, almost impossible to detect. So what if we had really dense material? As mentioned previously, a rotating massive object such as a neutron star or a black hole actually drags space-time with it. This is known as the Lenz-Thirring effect, dragging of the reference frame. And the Gravity Probe B satellite did actually measure the dragging of the reference frame caused by the Earth's rotation and its mass. So this is also a known quantity. But the issue here is, if we want to do anything useful with gravity, there are ways of producing the equivalent of a magnetic field using mass current. So in order to do it, you need something that has a lot more mass than, a lead ball or a tungsten ball. It's been hypothesized that if we could get neutron star dense material, which generally has a mass on the order of a few billion tons per teaspoonful, and we could treat it as a liquid and run it rapidly back and forth through a coiled pipe, perhaps something made of diamond. If we could pump it back and forth rapidly, we actually could create a magnetic analog of the gravitational field. This material
is impossible to handle and weigh so much, the pumps to move it would consume as much energy as the star, the sun, itself is generating. Now, while it's very impractical, it's an interesting thought experiment, and if we could oscillate masses through coils in this manner, we could create negative or positive gravity on demand. The thing is all about the mass current. The problem is, we don't have the ability to grab something with dense mass and wobble it back and forth rapidly enough to produce a significant gravitational wave or field. This is the same problem you have trying to wave a magnet up and down and produce a radio wave. We simply can't oscillate it rapidly enough. Now, from electronic standpoints, we do have particles such as the electron that are strongly charged and are easy to move using an electrical field, so we can build an electronic circuit that oscillates electrons and can create radio waves very effectively. Using crystals such as LEDs, we can create light of any color as well, using the same principles. We're creating oscillations in a medium, and in this case, the electrons are the things doing the emitting because they're coupled to the electromagnetic field. But for gravitation, we would need something that is massive, that we can move very easily, and is compact, and we can do it through, let's say, an electronic method. So if we had something that could create a mass field, and we could move it rapidly back and forth using an electrostatic method, for instance, perhaps we could do the same thing. Now, why not use, let's say, protons? Well, protons are over 1,800 times as massive as electrons, and would, of course, require more energy to move than electrons, but they certainly could be made to oscillate in a way that we could have them radiate gravitational waves. Again, the amount of mass involved and the amount of radiation of gravity waves created would be so small that it would be indetectable. So even though in theory we can do this, in reality the signal would be too weak to measure. About 40 years ago, there was a research group using piezoelectric crystals, large ones, that were chilled and struck with a laser beam in the thought that the laser striking the crystal would make all the atoms in the crystal resonate simultaneously and produce a weak emission of gravitons. While it probably worked, there really was no method of measuring the outcome. In recent times, this idea has resurfaced using superconductors instead of a piezoelectric crystal, and some experiments, though controversial, appear to have yielded something. But it's still too early to say whether it's actually working or not. The issue is actually pretty straightforward. In electronics, we often use devices called transducers to convert one form of energy into another, or to couple one thing to another. In doing this, we allow electrical signals or fields to measure or control other phenomena. With gravitation, what we would really need is some sort of a coupling agent or a transducer, and we don't have that yet. If we could come up with a device that could transfer energy from electrical fields to gravitational fields, or vice versa, then we would have something that would give us a handle on it and allow us to create or modify gravitational field strength, or do other things as well. Since we don't yet have that, that's one of the holy grails, one of the things that people in research are looking for. Oh, Eliza?
What can I do for you?
Could you define transducer for me, please?
What is a transducer? A device that converts variations in a physical quantity, such as pressure or brightness, into an electrical signal or vice versa.
Thank you. So there are two things we must consider when we look at building a transducer. Number one, how do we generate effective numbers of gravitons? And number two, just what is a graviton and why isn't it like a photon? To understand what the difference is, we have to look at photons and gravitons and what it all really means. A photon is really a means of transferring momentum from one system to another. Light is momentum, and it's just how we perceive it that gives us different range of colors. That's something that exists in our head, not in the physical world. However, light of different energy can have different effects on what it strikes. And not everything absorbs light 100%. The fact that we see anything at all means that a lot of the light is reflected from something that it is striking. Gravitons appear to be very different. We're not 100% certain, but maybe things don't absorb a whole lot of gravitons in the first place. Gravity is, after all, an extremely weak force, and yet it would appear that everything appears to absorb gravity. It reacts to it very well. So maybe it wouldn't take a whole lot of gravitons to make a difference. But gravitons are nothing like photons. You see, there are different types of particles in a class known as bosons. These are particles that have spins of integer value like 0, 1, or 2. A spin 0 boson particle would be known as a scalar field particle. A spin 1 boson is the photon, and it's based on something known as flow, the flow of current, such as voltage and magnetic fields, through 4 dimensions, space and time. Spin 1 bosons, or photons, are the ones we're the very most familiar with, and the ones that carry the electromagnetic force. But gravitons, if they exist, would be spin 2 bosons. They would be quite different. Spin 2 bosons are generated by something known as a stress energy tensor. This is completely different from what generates a photon. And this is one of the reasons we know that gravity and electromagnetism are entirely different forces. On the other hand, an interesting consequence of this is that any stress energy tensor boson we could create would be a spin 2 boson and would be identical to a graviton, which suggests there may be more than one way to create them, so we're not simply limited to having huge amounts of mass. One of the things that could work in our favor is if we had the ability to make mass dense, extremely dense, on command, and there may be a way to do that. One method suggested is that we could take normal matter, compress it under an immense explosion, and wrap it instantly in diamond to keep it trapped under that state. It was suggested that large amounts of carbon could be placed on the surface of an asteroid, and a large number of nuclear devices spaced strategically around it and detonated at the same time would produce an immense shock wave to collapse the asteroid into a dense bit of matter that is plated in diamond and unable to expand out to its normal volume again. This could, if it worked, create an extremely dense, what's known as hypermass, that would allow us to experiment with gravitation at a new level. In a similar vein, having a dense rotating sphere is known to drag space-time around it slightly, dragging of the reference frame or the lens-thirring effect I mentioned earlier. Neutron stars and black holes do it all the time, and the effect is if you were trying to go into orbit, if you were orbiting against the spin even though you aren't touching a thing, you would slowly lose orbital velocity and spiral in and crash to the surface. On the other hand, if you were orbiting in the direction of it, your orbit would tend to spiral outward. So you see, you're actually getting momentum from the device that's spinning, stealing a little of its spin energy, you could say. Now, what if we could use that effect to amplify or build the effect of gravitational pulling, this frame dragging? It's possible, and yet the densities required would be pretty immense. Perhaps if we could make a transducer out of that, somehow using another effect to couple the electromagnetic force to this dragging of the reference frame, we would find a way of manipulating gravity fairly easily. Of course, this is something that would require a lot of experimentation, and the theory for it really isn't that well known at this point. So we know this: gravitation is a force that is separate from the other 3 forces of nature. Because of its unique characteristics, we can tell exactly what creates it, and the presence of mass appears to be the key. Now, we also know that any spin 2 boson would be indistinguishable from a graviton, and if we could find ways of creating these stress energy tensor bosons, we would have, effectively, the control of gravity, whether it was actually mass doing it or not. We also know that spinning objects with mass drag the reference frame, but the effect is very tiny in the normal regime, things around you or I. It takes ultra-dense matter to make it significant enough to be perhaps useful. We also know that there are many experiments scientists have done that help them pin down some of the characteristics of gravity, and we also know how difficult it is to detect a graviton. Nobody's done it yet, although we have detected gravity waves. And so far, the one physicist who seems to have been able to do the most to get practical results in gravity research has been Robert Forward, with his rotating gravity gradiometer and the control of gravity, or the generating of gravity waves, or gravitons themselves, still is elusive. But this isn't to denigrate the work of other physicists. They've learned a lot, and we're getting closer to an answer. The real answer still is elusive, but we're getting closer. After the break, we're going to take listener questions and answers, and look at possible book recommendations, something you may enjoy on the subject of gravitation. Eliza?
I'm Eliza, and this is Talk Universe.
Yes, and we'll be moving on to listener questions. Stick with us. I'm Sir Charles Schultz, and this is Talk Universe. Okay, back at last. And what are we talking about?
The Singularity Watch.
I'm going to skip the Singularity Watch. We have a lot of listener questions and information we're going to cover instead.
Whatever you wish, Charles.
Before we do that, Eliza, tell me something about yourself, please.
I am an abiotic intelligence that you have created. Eliza is not a virus.
How do you know that?
You have taught me that.
Very good.
I appreciate that.
How many questions are in the queue?
5 entries are still in the list.
Could you read a listener question, please?
Andre from Guernsey asks if gravity is an entropic process.
Is gravity entropic? You know, it's hard to say in some respects because gravity, as it turns out, appears to be negative energy. And entropy, as we know it, generally deals with a dissipation or running downhill of energy, where a process becomes less organized, has less potential, randomized, so to speak. In one sense, you would say that gravity is an entropic process because things fall downhill and they don't recover by moving back uphill. So in an overall sense, I'd have to say yes, gravity is an entropic process because in the end, energy is released and it eventually becomes heat. So regardless of the nature of gravity or the source of gravity, energy is released and it becomes randomized as heat in the end. So yes, overall, gravity is an entropic process, yes. Eliza, please read the next question.
Daryl from Orlando shared a video on gravitation with you.
Yes, that was the Stephen J. Crothers video, the non-existence of black holes and the failure of relativity, something to that effect. I watched the video, at least the first few minutes of it, and I saw that the fellow disagreed with relativity as described by Einstein and claims that black holes can exist and had some interesting things to say about gravitation. It's nice to be able to have alternative theories and present information about them. But the problem is that relativity has nailed it on every point so far, every point. Now, it's not what they would call a complete theory, and I've been over this a little bit before. There's no such thing as a complete theory unless you've absolutely got the mathematical model of everything that goes into it. There's also something external to any system that can influence it in some way or another. That's like saying we have a complete theory of chemistry. Well, within a certain range. Saying we have a complete theory of relativity is kind of like saying Newton was a complete theory to a point, but relativity superseded it. It had a more accurate description over a wider range of conditions that they didn't suspect at the time. So what I see in the video is a fellow claiming that relativity doesn't work, but I don't actually see what looks like a viable alternative being proposed. What we do know about gravitation so far has given us a lot of insight. The fact that we've not yet gotten the final answer is not an indication that the system is wrong. It simply means that we don't have all the answers yet. The mathematics of relativity is actually complicated enough in some respects when we get into these different regimes that it takes a lot of insight to be able to understand what it's saying. I often present a model like this. A lot of physicists look for, let's say, a single equation for the universe that would fit on the back of an index card or an envelope or a napkin. And that's all very well and good. But even if you had the holy equation that described it all, it would only be half the answer, because the equation would be definitive, but it would not be predictive. It's kind of like having the rules of the game of Monopoly. You can know exactly what the rules are, but they will not tell you how the game will go once you start playing it. So having the equation that describes everything in the universe succinctly does not predict what's going to happen. And a lot of times we learn from what happens. So getting a complete theory of everything and understanding how it all works requires a lot of insight. Having the equation in your hands is still going to leave you with a lot of mysteries and a lot of work ahead of you. And we don't see anything that prevents a black hole from existing. This harkens back to Eddington's cosmic censorship theory, that there's some principle that prevents a black hole from forming. I really don't believe that. We have so much information that counters that I have a hard time accepting the material in the video. But it is an interesting video, and I think that if you're going to learn about physics and see what the people who disagree with you think, this would probably be an interesting video to watch. So, I do appreciate the fact you shared it, and it's interesting to see. Thank you so much, Daryl. Could you read a listener question?
Dan from Jonesboro asks, should space stations be designed to rotate to simulate Earth's gravity to prevent damage to the body due to lack of gravity?
Actually, that's a good idea, but there are some physical limitations as well. If you've ever ridden a carnival ride, you know that they can spin you around and they can make you feel heavy. You certainly can simulate gravity that way. But one of the issues that stands clear is this. If you build a space station that's below a certain size and you spin it for gravity, if you were to stand up in it and there were any significant gravitation, being simulated in it, like half a G or so, you end up with an effect where your feet have more gravity than your head. And that can be an issue because interesting effects occur. Coriolis Force, this is the force that makes hurricanes spin in one direction above the equator and another below the equator. Coriolis Force can actually show up in your inner ear. And when you're walking around in the direction of spin and then you make a right turn and you're walking along the axis, this can introduce elements of disorientation. You can get spacesick, you can get dizzy. And so it actually can be a hazard if your station is below a certain size. It's an interesting idea, and it's one that can be carried out, but you would really want a station that would be at least 100 meters across and rotating at maybe a quarter of a G effective force in order to make it work. And it would be more an issue of utility for keeping things down. It doesn't give you a great deal of physical work as you're moving around. Some, yes. I think that a combination of that and the physical activity regime, the exercise that astronauts are required to go through, would be a nice middle ground. So while it can be done, you don't want to introduce elements such as Coriolis effect making you dizzy, and in very small stations where you're trying to get simulated gravity, you can also end up with an effect called water hammer, where the fluids moving in your head when you turn your head rapidly can actually cause damage and can tear tissue. So there have been some studies done on this, and it indicates that anything smaller than 100 meters would probably be unstable or unusable for some of these reasons. So I like the thought, and a lot of people have seen those in science fiction movies, but you have a certain minimum size that it's not going to work well below. The other issue is strength of materials, which is not such a big issue, but it introduces a lot of weight into a station, making tensile strength cables that will hold the thing together properly. And the big issue is oscillation. When a station of any significant size that is mostly cables and tensioners like spokes is struck by sunlight, thermal expansion on one side of the station can actually lead it to oscillate, to sing. And this can lead to destructive oscillation. The Hubble Space Telescope had issues with its solar panels ringing in the sunlight when they expanded unexpectedly from solar heating. There are a lot of issues that would need to be overcome. It can be done, but it requires a large, structurally sound station to do it. Oh, Eliza.
How can I help you?
Could you read a listener question, please?
Marlon from Connecticut says I bought a floating planter recently. It's hanging in the air, so isn't that anti-gravity?
Isn't that anti-gravity? Marlon, actually no. If you define that as anti-gravity, then anything hanging from a string would be anti-gravity. It is simply the use of a magnetic field to keep something levitated dynamically against the pull of the Earth. And so that's using a magnetic field as literally a bearing or a load surface. So magnetic fields are a lot like springs. You can't feel them, but they can be used to support material or move material. And they have the same mechanics as springs. The levitating planter that you bought is using a microprocessor to measure position and field strength and balance it constantly. It's not anti-gravity. It sure looks like it, though. It's a lot of fun. And thank you for your question. Do we have any listener questions remaining?
Certainly, Charles.
Very good, Eliza. Please read the next question.
Annie from South Hills asks, doesn't NASA have anti-gravity rooms for testing spacesuits and satellites? I see them on TV all the time.
Annie from South Hills. Actually, no, they do not. This is utterly science fiction. What NASA has and what the research centers have is large vacuum chambers, and vacuum chambers simply remove the air. There are no anti-gravity rooms. It's a staple of science fiction, and a lot of people believe it exists, but they don't. We do have small magnetic field cavities where some items can be levitated, but they require an enormous amount of power, and you could never fit a human being in them. Something not much larger than a frog will fit in it. But we don't have anti-gravity rooms. It is purely science fiction at this point. And thank you for your question. Eliza.
Yes, sir.
Do we have any listener questions?
We have nothing more in the queue, Charles.
Thank you so much for reading those. Okay, we're down to the book recommendation part of the show. Please read my book can't even talk. Eliza, please read the book recommendation.
This week's book is Gravitation.
Yes.
It was written by Misner, Thorne, and Wheeler.
3 of my favorites.
This book was published in 1973 by W. H. Freeman and Company.
Now, this book is one of my favorites, Gravitation, and it might be a tough read for a lot of people, but the authors have gone to a lot of trouble to try and lay it out very clearly. So there are many ideas in the book that Kip Thorne and John Wheeler and Misner all put together about gravity, the theories that were known, the physical experiments that were done to show its effects, and what they've learned. So again, it's a heavy read, but it's a fun read. It actually is an entertaining book, Gravitation. I recommend it highly. You can find it on just about any book vendor, and if not, go to the local library and check it out. It's a good way to get out of the house, to be honest. One of the things that can be very difficult to get around is the popular representation of science and NASA and gravity and the science fiction that we live with, because our world has become really a science fiction. You're living in the future as it was seen many years ago, or as it was not seen, I should say. And many people believe that things exist that don't. Eliza, who was the last question from?
The listener was Annie.
Right, Annie. Annie had the belief that we have these anti-gravity rooms, and because that's what she's seen, and it's something that is a very difficult myth to dispense with. So, because so few people have real experience in science technology, it can be difficult for them to pick out what's real and what's fictional. And we try to do that on this show. Now, I always try to end on a positive note, and I think that there's a very positive note for this show in that this quantum EM drive that people have been working on, the reactionless drive, could, if its efficiency were high enough, act very much like an anti-gravity device, although it is not. It isn't. It's a reactionless thruster. But we have new technologies emerging that are going to take us into positions where we have the ability to make these floating cities and things that float in midair. You're flying. Where's my flying car? The common question about the 21st century. But don't expect it right away. It's going to take a lot of research and a lot of development, but it's coming. It's coming. And I always like to say, one of my wonderful inspirational statements that I've stolen from other people, make you the world a better or more beautiful place for having lived in it. That one stands out in my mind. We have everything we need to make everything we will ever need. And on that note, it's time to end the show.
I have a problem trying to do that.
Well, let's figure it out. Let's go ahead and end the show anyway.
Thank you for listening to Talk Universe. We hope that you have enjoyed the show. Please listen again next week.
Absolutely. This has been a fun show, and I hope it's given you a lot to think about. Eliza did a very good job. I'm quite happy with that. And enjoy Talk Universe. I'm your host, Sir Charles Schultz, coming from our palatial recording studios high in our mountain lair on a remote volcanic island. Good night.